Okay, so far the name distributions in the continuous category that we've seen, we've done uniform, we've done normal, and now lecture 15 we're going to do the exponential. So when are the scenarios you use the exponential? Well, to some extent, anytime we're modding time to an event. So classic ones, survival times, time to decay for radioactive atoms, time to failure for electronic components. So we've got a random variable and we're measuring the time once we start observing it until we get a failure. So the exponential distribution is this one. This is lambda e to the minus lambda y. And we're assuming that y, because it's a time, is greater than or equal to 0. Lambda has to be, for this to be a valid probability mass function, greater than 0. And generally lambda is our rate parameter. You will occasionally see a different form to this, what we sometimes call the beta form. So let me just write that out for you. So that would look like f of y, and now it would be 1 over beta e to the minus y over beta. And obviously again this is for y is greater than or equal to 0. And that's called the beta form. We're going to teach the lambda form in this one because it's the one that most naturally goes towards what we call the Poisson process, and the one that we sort of generally use in probability. So here's the mean and the variance. So the expected value of y is 1 over lambda, and if we think about lambda is the rate of events per unit time. So the times the event, that 1 over sort of makes sense. The variance is 1 over lambda squared, and the moment generating function is lambda over lambda minus t. Now the interesting thing is this has what we call the Memoryless property. So let's think about what this says. Let's say I've been observing my event and I know that no events happened in time A. I can say, well, what's the probability that my event now takes altogether A plus B? So we've just had, amount of time A, there's been no events, and I start counting now on my time how long it's going to be. The probability that y is greater than a plus b, given that y is already greater than a, is just y is greater than b. It's almost like at any point, if I've got, I've been watching for an hour, and then I stop at that point and say, what's the probability I get an event in the next hour? It's like I restart the clock. It doesn't know that I've been watching it for an hour. It doesn't care. As soon as I start my new thing, you have this sense that once I start observing at any point, the probability of happening in the next hour will always be the same. And we call this the Memoryless property. And if I remember rightly, in either the assignment or the tute, you'll actually show this. So let's actually use the exponential distribution. Let's have an example. So y is the time for a hard drive to fail. It's known to be exponentially distributed with a mean time to failure. So we haven't been given a rate, we've been given a mean time to failure of 24 months. We're going to calculate the probability the hard drive will last less than 1 year, and it will last more than 3 years. I'm also going to calculate the median time to fail. So we haven't discussed the median before, so we'll look at that as well. So what have we been told? Well, we've got our random variable, we'll call it y, and it's an exponential and we need to know what it is. Well, we know that the mean time to the event is 24. So think about it, the rate, lambda, you're expecting that it will be one event per 24 months. So it's 1 per 24. Okay. So what's the first thing that we need to do? We want the probability that y is less than or equal to 12. Now the one thing to be very careful of, a classic exam trick, is to mess around with the units and be jumping from years to month, etc. Make sure that the values you're calculating are in the same units as the rate as the mean. So you're comparing like with like. So we are just going to integrate from 0 to 12. Let's put in our distribution, our lambda, 1 over 24, e to the minus y over 24 dy. Well, if you remember your exponential, and if you don't, go and remind yourself of it. That's going to be minus e to the minus y over 24 from 0 to 12, which is minus e to the minus a half, because we've got 12 divided by 24, minus minus, so plus e to the 0. That's 1 minus e to the minus a half. As I said, if you're not sure how to integrate an exponential distribution, go and quickly check it on Wiki or equivalent. What's the next one we want to do? We want to do the probability that y is greater than 36, which is 1 minus the probability that y is less than or equal to 36. Convert that to a CDF, which is 1 minus the integral from 0 to 36, 1 over 24, e to the minus y over 24 dy. And if you do that integration, have a go yourself. That's 1 minus e to the minus 3 over 2 plus 1, which ends up being e to the minus 3 over 2. Now the median one. Well, what is the median? Well, if you think about a distribution, so let's assume we've got our exponential like this. This is what our exponential looks. So we've got our y, this is our f of y. Your median is the point such that the area less than it is 0.5. And obviously, the area greater than it will also be 0.5. So what do I want to do? I want to integrate from 0 to m, which we'll denote as our median, my PDF 1 over 24 e to the minus y over 24 dy. I want to solve this such that I will get 0.5. Well, let's do that integration. That's going to be minus e to the minus y over 24 from 0 to m equals 0.5, which is going to be minus e to the minus m over 24 plus 1 equals 0.5. So let's go over here. If I rearrange that, I'm going to get e to the minus m over 24 equals 0.5, which I'm going to write as a half, which we'll see for in a second. So I'm going to take log to the base e on both sides, so I get minus m over 24 equals the log, this is of base e, of a half, which is minus m over 24 equals minus the log of 2. So eventually I get m equals 24 log 2. Remember, that is log base e. If you're not sure how I got from there to there, well, remember that we can write that as the log of 2 to the minus 1, which equals minus the log of 2 by the log rules. So there we are. There's our exponential. An interesting thing with these distributions, there's more than one distribution, we'll see the gamma next time, that's also useful, that are looking at modelling time and time to event, is sometimes what you really want to do is you want to sort of go, well, I don't know what's the probability I'm going to fail in the next year. What's my instantaneous probability of failure at this point? And we denote this by our hazard function. So let's think about our hazard function. So we're going to denote it as hy of y, and it's going to be a conditional probability of failure. And what it's saying is, what's the probability I fail in the next small little bit? So I'm at point y, and I want to say, what's the probability I fail between now and y plus delta? So I'm thinking about this tiny, small little amount of time, a minute or a second. I'm going to assume that I've actually got to the point of being at y. So I'm saying at y, given I'm at y, what's the probability I fail in the next instantaneous bit? And what I'm going to do is I'm going to take this as a limit as delta. So this is going to get me my instantaneous rate of failure. And you can show that this is your PDF divided by 1 minus your CDF. And you'll find if you do that calculation for the exponential, you will find that it's constant and that it's equal to lambda for all values of y. So with my exponential, with my rate of lambda, my instantaneous rate of failure will be lambda. Now, that doesn't make sense for modeling certain things. We know that as certain things get older, the probability they fail increases, or maybe it decreases. But this idea of a constant is sort of the base case for modeling sort of time to failure of stuff. So next time we will look at the gamma distribution, which is a more general version of the exponential. Okay, see you next time.